Okay, now that we have everything, we are fully equipped to work on systems whose energy are conserved. Let's see what is happening. So let's, for now, go back to what we had before. The principle of work and energy. Remember, this principle is general, doesn't matter the class of force, conservative, non-conservative, always works. You had T1 plus sum of all works done by all forces from point 1 to point 2 gives you T2. Now, here is the funny thing. If all forces are conservative, if all forces in a system, within a system, are conservative, see what happens. Why do I do that? In that case, we saw we can find the work of all these forces as writing it as the difference between the potential energies. And these include all forms of potential, gravitational and elastic and so on. So gather all your potential energies at point 1, gather all your potential energies at point 2. The difference gives you the total work. Now combining these two, you have T1 plus V1 minus V2 equals T2. And rearranging some stuff, T1 plus V1 equals T2 plus V2. In other words, what we have, T is the kinetic energy, V is the potential energy. This is the total mechanical energy of the system at some initial instant should equal total mechanical energy of the system at another time. So this is a very useful, extremely useful, I cannot stress it enough. If all forces within the system are conservative, then total mechanical energy remains conserved or constant. And this is extremely useful when we don't know or we don't care what happens between two states of the system. All we care about is some initial state we know information about, some final state we are interested in. What we can do is calculate initial energy compared with the final energy. If all forces are conservative, these two has to be equal. And that immediately gives you a lot of information about relationship between speeds of different particles inside the system and their relative location to each other. So extremely useful. And something I should add here is, I don't know if I mentioned it, maybe not, I don't think so, that conservative forces, well, as the name suggests, conserves energy, conserves total mechanical energy. Non-conservative forces usually either add energy to the system, as in the case of external forces, or reduce the energy of the forces, often in form of dissipated heat. So if you don't have energy change all forces are conservative, total mechanical energy remains conserved, and only forms of energy convert to one to another. Either potential energy conserves or transforms into kinetic energy. That is the case, for instance, when you have an object falling through gravity. It picks up a speed as it comes down, meaning that its potential energy that was higher here is converting to kinetic energy. Another good example that I like a lot is when you have an object attached to a spring. As you pull the spring back and let it go, the object oscillates back and forth. On the two ends, you have maximum stretch of the spring. So you have a lot of high potential, or the only thing you have is potential energy. And in the middle, as the object passes through the center, you only have kinetic energy. So your kinetic energy and potential energy oscillate back and forth. But the total remains conserved. And the last thing I wanted to say here, obviously, the question is, what happens if you have both conservative and non-conservative forces? Or in other words, if non-conservative forces exist. If conservative forces exist. Remember that always, if that is the case, what happened? Principle of work energy applies. This is always the case. Doesn't matter what kind of force you have. Conservative, non-conservative, the principle always holds. But if you want to be fancy and cute, what you can do is separate the total work of conservative forces plus work of non-conservative forces. And as we saw, this is V1 minus V2, exactly the same thing as you did before. What you end up with is T1 plus V1 plus sum of all non-conservative works equals T2 plus V2. In other words, if this is total mechanical energy E1, total mechanical energy E2, these non-conservative forces either add to your initial energy, gives you the final energy that is bigger, or essentially eat into or dissipate your total energy, gives you a smaller final total mechanical energy. And that is the case, for instance, when you have a box with some initial velocity on a rough surface. Initially, you have some total energy, and as you let it go, the box eventually comes to a stop. And what happens in between are these dissipative forces, friction, reducing the total energy of your system until you end up with zero mechanical energy. So I think that is all I wanted to say. Let me look at my notes. Yeah, I think that's all. That's good enough. This method of conservation of energy hugely simplifies the problem. Many of the problems, not every problem. Some problems that are, well, not impossible, but very difficult to calculate by hand becomes piece of cake using the concept of energy. So we'll see a lot of examples of this in class, and I'll see you soon.